It begins as unyielding stone, yet ends as a material lighter than air. Each year, global production weaves over 8 billion square meters of this mineral wool into existence, a vast blanket destined to insulate and soundproof millions of buildings across the planet. The transformation itself is a marvel of modern engineering. Inside the world's largest mineral wool facility, seemingly worthless chunks of rock are meticulously processed into one of the most effective insulation materials ever conceived. It was a divine gift, woven from volcanic fire and Pacific winds. A millennium ago, deep in the Pacific, a remarkable material was born on the Hawaiian Islands, a land forged in the ancient struggle between fire and water. Here, streams of molten lava, stretched thin by powerful gusts, cooled into delicate fibers that intertwined to form a natural, insulating blanket. According to legend, these were the very hairs of the goddess Pele, torn from her head with each violent eruption. For generations, Hawaiians used this sacred gift of nature to protect their homes from the elements. In the early 20th century, scientists rediscovered the extraordinary properties of this volcanic material. And from their knowledge, modern rock wool was born. But to insulate millions of houses, the lava of Hawaii alone was not enough. Humans had to recreate the forces of nature through industrial processes, a solution that carried its own environmental price. Across the United States, states with large basalt deposits, such as North Carolina, Missouri, and Utah, became the main sources of raw material for this massive new industry. It begins as ancient, unyielding stone, destined to be spun into a cloud of delicate fibers. The journey starts with the raw material itself, basalt and dolomite, hard minerals prized for their ability to endure extreme heat and their wealth of essential compounds. Deep within the open-pit quarry of Cardinal Aggregates in Ohio, the earth yields over 700,000 tons of this stone each year. Before the basalt can be reached, colossal excavators and articulated haulers must first strip away the overburden. This soil is carefully stockpiled, set aside for resale or for the eventual reclamation of the land. For every 10-foot section of earth peeled back, a staggering 1,600 tons of raw basalt are revealed. With the rock face exposed, the next phase begins: drilling and blasting. Powerful rigs carve into the stone at a rate of nearly 5 feet per minute, etching a precise grid of shafts across the designated blasting zone. Between 15 and 30 of these holes are then meticulously loaded with explosives. Each charge is sealed and wired into a controlled firing system, all under the watchful eyes of blasting engineers. A single, controlled detonation unleashes the power to fracture between 15,000 and 25,000 tons of raw stone in an instant. The newly fractured rock is immediately hauled to a crushing plant, where massive blocks are systematically broken down into more manageable pieces, each smaller than 10 inches. The processing plant refines the material further, ensuring it meets exacting technical specifications, and every bucket is electronically weighed before being loaded. On the busiest days, a constant stream of over 400 truckloads departs the quarry. This procession carries between 8,000 and 9,000 tons of stone daily, destined for manufacturing facilities. From these very blocks, the next stage of melting and spinning will transform the rock into millions of fine mineral fibers, the foundation of modern insulation. It arrives as raw, shattered stone, born from ancient volcanoes. It will leave as a silent guardian, a shield woven from fire itself. Heavy-duty trucks deliver their payload of basalt from the quarry, marking the first step in a vast industrial transformation. As metal gates swing shut, clouds of dust billow into the air, and the raw stone thunders onto conveyor belts. Beneath the factory's cool blue lights, gray boulders cascade into storage hoppers, creating a steady, flowing river of rock. Stones of a uniform size are sent directly to the processing line, while irregular chunks and impurities are diverted toward immense crushers. Moving along the batching conveyor, the stream of basalt is evenly sprinkled with glossy black particles of coke. This addition serves a dual purpose. It provides the powerful heat needed for the furnace, while also adjusting the material's chemical makeup. This careful recipe helps the basalt melt faster and more uniformly, preparing it for the inferno to come. The journey continues into the heart of the furnace, where the mixture of basalt and coke faces temperatures soaring above 5,800 degrees Celsius. In this crucible of extreme heat, everything dissolves into a glowing red torrent of lava. This molten stream, rich with silica, alumina, calcium oxide, and magnesium oxide, becomes a thick liquid nearly identical to volcanic magma. As the fiery flow pours forth, sparks erupt in every direction. Figures clad in ceramic fiber suits and metal masks step forward to monitor the conditions, their forms silhouetted against the intense glow. The channels and pipes guiding this molten river are forged from heat-resistant steel and lined with special refractory bricks, engineered to contain the raging sea of fire. These furnaces operate non-stop, 24 hours a day, 7 days a week, because a shutdown not only consumes enormous energy to restart, but also damages the refractory lining and risks the lava solidifying on the walls. From the furnace, the stream of incandescent lava is guided onto high-speed spinning wheels. As the molten rock meets the rapidly rotating surface, it is flung outward, stretching into fibers thinner than a human hair. A simultaneous blast of hot air follows the spin, carrying these delicate threads outward and cooling them instantly in midair. This rapid cooling locks in their slender yet remarkably tough structure. The result is a delicate rain of mineral fibers, which settles into a light, fluffy mat. This newly formed material possesses extraordinary heat resistance and powerful sound-absorbing properties, a stark contrast to the solid rock from which it came. Immediately after their creation, the rock fibers are collected by a current of hot air and laid gently onto large rotating drums or wide conveyors. Layer by delicate layer, the fine strands accumulate, building up into a continuous, flowing blanket of mineral wool that stretches across the production line. A system of powerful fans and suction ducts is precisely calibrated to distribute the fibers evenly, preventing any thick or thin spots from forming in the growing mat. At this stage, the material remains soft and billowy, resembling a flowing sea of white fibers. But the initial streams are only a few centimeters thick, far too thin for their final purpose. The flow of rock wool moves onward to the layering stage, where the mats are methodically stacked one atop another to build up the required depth. This process can increase the sheet's thickness from just a few centimeters to as much as 20 to 30 centimeters, depending on the final application. Once layered to the correct thickness, the mineral wool mat advances into a massive roller press system. Here, an even distribution of pressure is applied across its entire surface, compressing the loose fibers into a dense, stable sheet with precise dimensions. The pressure exerted by the rollers is carefully calibrated for each product. The thinner and denser the final sheet, the greater the force required. Simultaneously, mechanical arms press against the edges of the conveyor, keeping them tight and preventing the material from spreading outward. This dual action transforms a soft mat into a firmly compressed block of mineral wool. The final product has a uniform thickness of about 8 to 12 inches, tailored to its specific industrial or residential use. With its structure now firmly compressed and stabilized, the mineral wool block proceeds through a high-speed cutting system. The first set of blades trims away the excess material from the edges, creating the straight, squared sides needed to fit a specific mold shape. Once these rough edges are removed, the block enters the main cutting line where sharp blades leave clean, perfectly straight sides. Additional cutters then descend, slicing the thick blanket into individual panels or blocks, each with uniform dimensions. Throughout this process, sensors track every cut, ensuring that the length and width remain consistent from one piece to the next. By the end of this stage, the once loose mat of fibers has been transformed into an inventory of neatly shaped insulation boards. Each block is cut into standard panels, typically around 24 by 48 inches, with a thickness ranging from a few inches for homes to nearly a foot for heavy industrial applications. The Rockwool slabs are now formed, but they must first pass a series of crucial quality tests. Part of this inspection involves checking their hardness, where pressure tests ensure the slabs can withstand mechanical stress without losing their shape or density. And because mineral wool is valued for both its insulating and fireproof qualities, a fire test is essential. A flamethrower blasts the surface, raising temperatures to around 1 to 200 degree Celsius. In a striking demonstration of its power, A person can sit directly behind the slab, comfortably reading a newspaper, completely shielded from the intense heat. After the rigorous inspection is complete, the finished Rockwool insulation boards are carefully wrapped in heavy-duty plastic film. Automated machines seal each block tightly, protecting it from moisture and potential damage during transit. The packages are then secured with an additional layer of shrink wrap, which keeps them stable when stacked for storage. Forklifts transport the finished bundles to tall warehouse racks, where thousands of units are stored in neat, towering rows. Finally, the insulation is loaded onto trucks and shipped to construction sites and industrial projects. There, the panels are fitted directly into pre-prepared wooden or metal frames. Workers cut the slabs to size and press them firmly into the cavities, ensuring no gaps remain. Thanks to their interwoven fiber structure, the panels hold their positions securely without requiring significant adhesives. This hidden layer becomes a protective shield, keeping buildings warm in winter, cool in summer, and safer from the threat of fire. From the dust of the earth and the remnants of our cities, a new form takes shape. The journey begins where trucks deliver the fundamental ingredients for creation, including minerals like sand, soda ash, borax, and dolomite. But the heart of the mixture is recycled glass, known as cullet, which composes nearly 80% of what feeds the furnace. This cullet arrives in two forms: plate glass from windows and windshields, and container glass from bottles and jars. A powerful pneumatic system unloads the raw materials, whisking them into towering storage silos that hold a 4 to 5 day supply, ensuring production never ceases. When the furnace demands a new batch, an automated system awakens, weighing each component with digital precision before combining them into a perfect blend. This carefully crafted mixture then embarks on a journey by conveyor, ascending to a feeder silo positioned directly beside the furnace. This smaller reserve holds a crucial 8-hour buffer, a strategic pause that allows the plant to resolve any issues along the batching line without halting the entire operation. From this silo, a water-cooled screw conveyor guides the raw mix into the immense furnace chamber, the very heart of the process. This hybrid furnace harnesses the power of both gas-oxygen firing and supplemental electric resistance, a design that maximizes energy and environmental efficiency. Inside this inferno, the glass boils at a staggering 1,400 degrees Celsius as flames sweep across the molten surface. The liquid glass then flows onward through heated channels, a crucial step that maintains the precise viscosity required for the next stage. It pours into a spinner, a device rotating at incredible speeds that forces the molten glass through thousands of microscopic holes, instantly forming ultrafine fibers. A powerful downward stream of hot air stretches these delicate strands, while compressed air helps regulate their length and aids in cooling. The newly formed fibers first pass through a ring that sprays only water, rapidly lowering their temperature. Immediately after, a second ring mists them with a proprietary biobinder, a specialized formula that is both colorless and free of formaldehyde. These coated glass fibers drift down into a forming chamber, where they are collected and spread evenly onto a moving conveyor belt, creating a continuous, unbroken mat. At this stage, the freshly spun fiberglass appears as a light, fluffy, off-white blanket. As it continues its journey, a liquid binder is sprayed on, appearing clear at first, but its passage through a long, hot curing oven triggers a chemical reaction, hardening the binder and changing its color to yellow, orange, or even pink, depending on the specific formula. Emerging from the heat, the wool is immediately compressed under immense rollers, transforming the soft, fluffy mat into a firm block of consistent thickness and density. The compacted block now enters the cutting line, where razor-sharp blades descend to slice it into panels of exact dimensions. A system of sensors and guides guarantees that every single sheet is uniform, perfectly sized to meet demanding building standards. In the final stage, these panels are wrapped in a protective film and tightly sealed, a barrier against moisture and damage. Forklifts then stack the finished bundles onto pallets, ready to be loaded onto trucks for their journey to warehouses and construction sites across the country. Within the United States, one particular brand's pink fiberglass has come to dominate the market, becoming its unmistakable signature. The company went to extraordinary lengths to protect this identity, successfully trademarking the distinct pink color and making the hue legally their own. Behind our walls, an unseen battle is waged against the elements. The world relies on two dominant champions in this fight: Rockwool and fiberglass, the most common insulation materials on the planet. Each one works tirelessly to shield our homes from the outside world. They are engineered to trap precious warmth during the biting cold of winter and to repel the oppressive heat of summer. These are the silent, fibrous guardians of our comfort, woven into the very fabric of modern life.